So now that we have a better understanding about acid and bases, we are ready to start doing calculations with them. And the first thing we have to understand is the equilibrium constant for water, better known as Kw. And what is that? Well, remember, every time we did the Bronsted-Lowry definition, we saw water grabbing a proton from the acid becoming hydronium. And we also saw water giving a proton to the base becoming hydroxide. So in other words, water was behaving like an acid in some instances, and it was also behaving like a base in other instances. That makes water amphoteric. So amphoteric is a substance that can behave like an acid or can behave like a base. For example, hydrogen sulfide is also amphoteric because it can still lose one proton, becoming sulfide. So that would be behaving like an acid. Or it can gain one proton, becoming sulfurous acid. So that's a good example of another substance that is amphoteric, meaning can behave like an acid or can behave like a base. So imagine then that water is always reacting with water, producing hydroxide or hydronium. That's a problem, right? Because that means the water, after millions of years, would be totally gone somehow. So that's not exactly like that. Out of every, let's see, 1, 2, 3, out of every 10 million molecules, only one molecule of water does that. So that's why it's not really a problem, because out of every 10 millions, only one molecule of water does that. So water tends to react with itself, producing hydronium and hydroxide. But since this is 1 to 1, it's going to produce also one hydronium for every hydroxide. And because the amount of acid and the amount of base are the same, they cancel each other, becoming water again, and that goes back and forward because it's an equilibrium. Because remember, if water is behaving like an acid, it's a weak acid because it's not one of the strong acids, right? It's not one of the 7. So therefore, it's an equilibrium. So when it's water all by itself, since the amount of hydronium and hydroxide is the same, we don't notice any changes on the acidity because it's neutral. It just behaves like pure water. Even though one of every 10 millions is doing that, they cancel each other. So what we call Kw is the multiplication of the concentration of the hydroxide produced times the hydronium times the hydroxide. And remember, I told you that it was only one molecule out of every 10 millions. That's actually 1 × 10⁻⁷, one of every 10 millions. So the hydronium is going to be 1 × 10⁻⁷. The hydroxide is going to be 1 × 10⁻⁷. So when we multiply those two together, the value for Kw is going to be 1 × 10⁻⁴. And this value is extremely important to remember. This tells us that doesn't matter what, the amount of hydronium and hydroxide will always be on equilibrium with that total amount. So if the amount of hydroxide happens to go up, the amount of hydronium will have to come back, so we always stay at that value. That value, as long as we are at 25 degrees Celsius, which is kind of normal, that value never changes, 1 10 to the minus 14 at 25 degrees Celsius. So we can use that to our advantage. So that's what Kw is. Because now we can say, okay, so I know that the concentration of hydronium times the concentration of hydroxide, as long as we're talking about 25 degrees Celsius, it always has to be 1 10 to the minus 14. What if I take pure water and I put some lemon on it? And we know that lemon is sour, right? So lemon is acidic. So that will increase that there. So I can say, so instead of being 1 10 to the minus 7, now it's going to be 1 10 to the minus 6, which is bigger. So I increase it, right? So according to this constant, it doesn't matter what, it has to give me 1 10 to the minus 14 at 25 degrees Celsius. In other words, if I take the Kw value and I divide it by the amount of the acid, that gives me the amount of hydroxide, which on this case is 1 10 to the minus 8. Because when I do 1 10 to the minus 8, which is the hydroxide, multiplied by the acid with the lemon added, which is 1 10, which we said we agree it was going to be 10 to the minus 6. All that together give me 1 10 to the minus 14, which is what it always had to give me at 25 degrees Celsius. So this is a powerful formula. Kw 1 10 to the minus 14 equals the concentration of the hydronium times the concentration of the hydroxide. If I change any of those two, the other one will have to change to give you always, always, and always 1 10 to the minus 14. So using that knowledge, let's work on this here. Well, before we do that, so hydronium and hydroxide, that's going to be altogether 10 to the minus 14. Same here. You should notice I just adding the numbers, because when you multiply powers, you add the powers. So this one is the one where they're exactly the same. That's what we call neutral. So whenever the hydronium concentration and the hydroxide concentration are 10 to the minus 7, that's neutral. Any number, since we're dealing with negative power, the smaller the number, the negative value, the bigger the amount is. So 10 to the minus side, 1 10 to the minus 5 is actually that, while 10 to the minus 9 is actually that, right? So the smaller the negative number, the bigger the value. That's what I was saying. So the bigger the value, if the bigger value is hydronium, that means that it's more acidic. If the bigger value is the hydroxide, that means it's more basic. If they are the same, that means they're neutral. So on the first one, the bigger value is the hydroxide, so this one is acidic. On the second one, the bigger value is hydronium again, so that's acidic. I believe I said hydroxide on the first one, sorry for that. The next one, they're the same, so this would be neutral. And the last one, the bigger value is hydroxide, so this one will be basic. So as long as we're dealing with the powers of tens, the smaller the negative number, the bigger the concentration is going to be. So with that in mind, go ahead and do that. And once you do with that, let's do this one here. So now we're gonna calculate. So given the hydroxide, I should be able to find the hydronium. Given the hydronium, I should be able to find the hydroxide because I know 110 to the minus 14 equals hydronium times hydroxide. So if I know any of these, I can use my math to find the other one. So the first one is 1510 to the minus 7. So the hydroxide, which is the other one, is going to be 110 to the minus 14 divided by 1.5 10 to the minus 7. And be careful, make sure you know how to use your calculator when you divide it by scientific notation. So 1 10 to the 14 divided by 1.5 to the minus 7. Let me do that again. 110 to the 14 divided by 1.5 to the minus 7. That would be I'm myself having problem with my calculator right now. Okay, I got it now. So each calculator is kind of a little bit different than others. Don't forget to put those negative numbers. So that's going to be 2, 4, 6. That's going to be 6.67 times 10 to the minus 8. For the second one, the hydroxide concentration is given, so that means I should be able to find the other one. And that's going to be 110 to the minus 14 divided by the hydroxide that is given. And that's going to be, 110 to the 14 divided by 2.1 to the 11. That should be 4.76 times 10 to the minus 4. And I think with those two, you should be able to see how it's done, right? So depending on which one you're given, you're looking for the other one. And it's always KW over the value given. So with that said, you should be able to do that. And once you're done with that, we basically have this concept down. So remember, the key equation is KW equals concentration of hydronium times the concentration of hydroxide. KW is 110 to the minus 4. So 110 to the minus 14, sorry, is hydronium times hydroxide. So if you need to find the hydroxide, the hydronium, you will do 110 to the minus 14 divided by the concentration of hydroxide, or vice versa. And with that, we're done with this part of the lecture. Next time we come back, we will begin covering the pH scale. So now that we know how to find the hydronium, dealing with a number with a lot of zeros, 10 to the minus 7, 10 to the minus 8, let's bring down to a very easier system from 1 to 14. So that's what we do when we come back. So see you soon. Take care.